Here's a replica of the Crookes tube used by J.J. Thomson at Cambridge University in the UK. Here's kind of the model we've been using, where the cathode's over here, the electron beam goes this way, here's your electric field right here, which is deflecting the electrons, and then here's your semicircular orbit that they take once they're deflected by a magnetic field later on. Here's what it looks like in real life. Here's the dome, and on this dome is where you have the fluorescent material so you can see where the electrons hit. Thomson continued to refine his experiment, and here is a replica of the third mass spectrometer that he used. And you may have come across this in the magnetism chapter where we talked about a velocity selector, which is going to select out the charged particles with a given velocity, and then over here is where you have the magnetic field that will separate the particles out due to their mass. So the ions come from this side, the electrons are, the free electrons are created here. They go through the electric and magnetic fields where their velocities are chosen, they get bent, and over here we have a detector where you can find the different particles and what their charge to mass ratio is. Now that Thomson had measured the charge to mass ratio of the electron, if the physicists could figure out either the charge or the mass, they would then know both quantities. His team made several attempts to measure the charge of the electron using water droplets in an electric field, and don't worry, we're going to talk about that in a few slides. Using that method, Thomson assigned a value of 1.03 times 10 to the minus 19th coulombs to the charge of the electron. As we showed earlier in the course, the charge on the electron is actually closer to 1.6 times 10 to the minus 19th coulombs. So although Thomson had the right order of magnitude, he had the 10 to the minus 19 right, the percentage error of his measurement was 54%, which is certainly not acceptable. But it was left until 1909 when a graduate student, built on many years of experimentation by many other physicists, and actually refined the method to come up with the charge on the electron in an afternoon. Then after more months of tedious experimentation, a more accurate value for the charge on the electron was found. The idea is pretty straightforward, and first we'll talk about how Thomson and others tackled the problem before this graduate student came along and just nailed the exact value. It's a pretty straightforward concept, and we've already done some work on this in the earlier chapters. An object, in this case let's take an object with charge q and mass m, will fall at a constant velocity if the sum of the forces in the y direction are equal to 0. So we have QE going up, mg going down. So basically, if QE is equal to mg, then the object will fall at a constant velocity. So why can't we just get a few electrons and measure them? Well, frankly, because they're too small to see and we don't know their mass. So what Thomson and other physicists decided to do was take water droplets and see if they could get them to float, or again move with a constant velocity with zero acceleration in an electric field. This way they can estimate the mass of each drop and then see what the charge was on each drop. By measuring a lot of drops, and this is a really huge number, this experiment could go on for days, weeks, etc., they could find the smallest charge and figure maybe that was the electron's charge. But the problem with using water is water evaporates, so the mass is going to change, so this experiment won't be perfectly accurate.